Hey everyone, this is Daniel, and you are watching a long-form guide on Kotlin Flows. So Kotlin Flows are a next step after you learn Kotlin Coroutines, for which we have another guide here on the channel and also on the blog. So in this video, we will learn how Kotlin Flows work, how to build and consume them in various ways, and how you can use inter-thread or inter-coroutine communication using Kotlin Flows. Trust me, after you learn Kotlin Flows, you will not want to go back because they're so incredibly useful. So obviously, the best way to make use out of this video is to write code with me, and whenever you need to refresh your memory, or if you want to refer somebody to this video, if they ask, where did you learn Kotlin Flows? You can refer them to this video. Also, you will have a written form at the blog with the link in the description by the amazing Ricardo Cardin. We also have all the examples in this video in written form with all the details step by step. So without further ado, I'm going to navigate back to my dev environment here in IntelliJ IDEA, where I have a little application that I called Flows with a fun main and with a bunch of hard-coded data. In this video, we will simulate a little IMDb-like application, and I have a bunch of data type definitions like ID, first name, last name, and actor, as well as some hard-coded actors for the famous Zack Snyder Justice League movie, as well as the Avengers, and we also have 3 versions of Spider-Man because that's how the movie industry works. So you can find all these data type definitions as well as the examples in the first code snippet of the blog if you want to check that out. Now, just as an experiment, I'm also going to put this exact code in the description itself, so it's as convenient for you as possible so that you don't have to check out the blog and figure out which code snippet to copy and so on and so forth. So you can expect this code as the starting point in the description itself. Now, because this object model contains all this data, and because I'm going to refer to these data types as well as the variables here in my application, I'm actually going to call this model thing my Flows app or Flows. And I'm going to move my main function up so that we have everything in the same place so that I don't have to refer to model.everything. So you can start with this code and then you can add your main method. Okay, back to flows. What is a flow? Well, a flow is a so-called reactive data type that does not necessarily contain values, but rather we say that it emits values of a certain type. For example, let me create a little value. So I'm going to have a val. Let's call this a flow as of type flow with actor. I need to import flows from the Kotlin Coroutines. So make sure you import the right one. And you can build a flow with a similar constructor that you use for lists. So just as you use list of, set of, map of, and so on and so forth in Kotlin, you can do flow of, and you can have a bunch of variable arguments here. So I'm going to import everything from the flow package of Kotlin Coroutines. So flow of, and you can have, for example, all of these, Henry Cavill, and so on and so forth. So I'm going to simply take all of these, paste them here. And these are my Justice League actors emitted as values in a Kotlin flow. You can also have flows defined as extensions from a list of items. So let's call it a flow version 2. So I'm going to say list of all these values, but obviously this is a list of actor. And with the package Kotlin Coroutines flow, we have extension methods for the most common data types in Kotlin. So you can say as flow. And this is enabled by the Kotlin Coroutines package. So this method obviously does not exist on lists, but it's available as an extension method. If we have a function that returns a value, we can create a flow from that using the asFlow function as well. So for example, let's call this singleton flow as, or a singleton function. And I'm going to define that as a function 0 to actor. And I'm going to create a lambda that emits, for example, Superman, Henry Cavill, and then I'm going to have let's call this singleton flow as singleton func dot as flow. And this essentially calls the function to emit the value, Henry Cavill. All right. Now, the flow and flow version 2 will contain these values, but they do not necessarily emit all the values instantaneously at the moment that I construct the flow. They will only emit these values one at a time in the order that I define them when I request them, which is why flows are consumed. And flows will emit these values when they're being consumed. So flows are consumed and will emit values at that time. And for this reason, a flow is a very different data type than a list, for example. So a flow of all these values does not necessarily contain all these things in some sort of data structure, and then you can process them as on a list, but this will emit the values, Henry Cavill, Gal Gadot, Ezra Miller, and so on and so forth, one at a time when I start consuming items out of this flow. And the most general way to build a flow is to use the emit function. So the most general way to build a flow is to say something along these lines. Let's call this Spider-Man. And I'm going to use all the values from Spider-Man, Tom Holland, Tobey Maguire, and Andrew Garfield, and not necessarily in that order. So Spider-Man, and I'm going to have the flow constructor here. So the flow function has a flow collector that has some extension methods. So for example, you can use the emit function. So emit Tobey Maguire, and then emit Andrew Garfield, and then emit Tom Holland. That'll be the chronological order, and this will emit Tobey Maguire, Andrew Garfield, and Tom Holland when these values are being requested. So in order for us to consume the Spider-Man flow, you will say something along these lines. You can say spiderman.collect, and the collector has a little lambda that you can use to do something with every value. So for example, print line it. So this is the way that we would collect a Kotlin flow. The only difference is that the collect function is a suspend function, which will make us turn this main into a suspend fun. And because this is a suspend fun, we need to put it outside, and I'm going to cut the JVM static thing, and I'm also going to ignore the args, and I'm going to say flows.spiderman.collect println it. So we can run this little thing. It will compile it very quickly, and we will have all the actors, Tobey Maguire, Andrew Garfield, and Tom Holland, being printed in order because we are consuming the Spider-Man thing, the Spider-Man flow one at a time. But these emissions, as I just mentioned, they may not necessarily be immediate or synchronous. They may take a little while to start to emit values. For example, I can say delay with 1000, for example, and add a little delay in between the creation of two subsequent values here in the flow. And in order for me to run the delay, I'm going to import that from the Kotlin coroutines. So Kotlin coroutines delay. All right. And if I run this application one more time, you'll see that these values will actually take a little while. It will take 1 second to emit all these values, which will turn this flow into a fundamentally concurrent data structure. This does not necessarily contain all these values, but this will emit all these values as dictated by the logic of the flow generation. And this opens a lot of possibilities. For example, you can listen when an item is being created or when the flow starts emitting things. So for example, you can say flows Spider-Man, and before collect, you can say on start, and you can have a zero lambda that can do something. For example, you can log the fact that you started the flow. So you can print line flow started. And when we run this application, we'll see flow started, and after a second, we have the rest of the actors emitted 1 per second. Also, you can do something on each element being emitted. So for example, you can say on each, and you can have a delay in between the emission of two subsequent values there. So you can say on each delay 1000. So I eliminated the delay myself, and I added a delay in between two subsequent elements. And the effect is going to be very similar. So flow started, and then all the actors emitted 1 per line, 1 per second. And also you can say on completion, you can say print line flow finished, which is what also signals the fact that this flow has terminated. So the flows do have an ending at some point, or the flows may be very long lasting. So you see here flow finished, but these flows can emit all these values in a while true, for example. So while true, you can have this emission, and this flow may never really end. But the while true is not an infinite loop in the sense that it will block the application, because all these flows are running on their own separate coroutines. So in this case, we're going to have all these emissions, Tobey Maguire, Andrew Garfield, and Tom Holland, emitted in a cycle. So look at that. We have all these actors emitted in a cyclical fashion with 1 second delay in between them. And at the same time, we can also do something else with our application. So these flows are fundamentally concurrent. So that's very interesting. We have these so-called lifecycle methods like onStart, onCompletion, and onEach that will allow you to insert any piece of logic when necessary. Okay. The next question is, what happens if the flow is empty? Or what happens if the flow throws an exception? What happens then? We're going to take all these questions one at a time, and we're going to add a couple more questions as we progress. So for example, what happens if the flow is empty? So let me create an empty flow. So actors empty flow as a flow. And I'm going to have the type actor here because otherwise the type inference will not really know what kind of value I want to emit because I'm not going to emit any value. So I'm going to say delay with 1000 and I'm going to leave it as such. This is a flow actor that doesn't emit anything. But if the flow is empty, I can then decide to do something. For example, I can say on empty. On empty, I'm going to emit, for example, Tobey Maguire. So on empty, I'm going to emit Tobey Maguire after this flow has, in theory, ended. And this on empty thing will return a new flow. So I'm going to, let's say, print something. So flow actor delay, something like that. And on empty, I'm going to print line, print. I'm going to say flow empty emitting something. And in this case, I'm going to have flows.actors empty flow and gonna keep it at that. So flow started, flow empty emitting something, and then we're gonna have the actor emitted after another second. So this is straightforward enough. Let's test what happens if the flow throws an exception. So I'm going to copy the Spider-Man thing, and I'm going to kill the while true, let's say Spider-Man exception, and I'm going to have this emit Tobey Maguire. And then after Andrew Garfield, let's say something went wrong in the application. So throw runtime exception. I'm going to say boom. Or doc awk happened. And in this case, the emission is not going to happen anymore because the throwing is going to interrupt the flow. Now, what happens when you run this little application? So when, say, Spider-Man exception without any sort of error handling, obviously the flow will interrupt and you're going to see a little stack trace, doc awk happened, and this will trigger the finish of the flow, which you can then handle in your application. So this stack trace occurs from the coroutine that emits the values or that handles the emission of values from the flow. And if an exception happens, then that will interrupt the coroutine and finish the flow, which means that the on completion will be run no matter what. Now, if you want to catch an exception, there is a catch. There is a catch function there. So look at how catch is both a function and a keyword in the Kotlin language. I absolutely adore that about Kotlin because you can use the words in different contexts. So if you get any sort of exception, you will emit Tom Holland, for example, by printing something wrong and we have hero to the rescue or something like that. And if we run this application one more time, we're going to see flow started and then we're going to have all these actors and then the doc awk happened and then we have this something wrong, which also emits Tom Holland as a result of catching this exception. Now, two mentions here that you may find quite straightforward or obvious. If you throw an exception in the catch clause or after the catch has been successfully handled, or for example, if you want to transform this flow to something that in the transformer throws an exception, that exception will not be caught. So I'm going to say instead of doc awk, some boom happened. In this case, we're going to interrupt the flow after emitting Tom Holland. So we have flow started, 1, 2, and then we have actor emitted, and then we also have the boom happened, which also interrupts the flow. So this flow interrupts abnormally because of the runtime exception that happened after the catch. So everything after the catch either booms or has to be caught again. So you can have multiple catch clauses. You can say catch again, and you can say print line, something bad happened. And in this case, the runtime exception will be caught by the other catch clause, and the flow will be terminating normally again. So you can add as many catch clauses as you want. Also, if you throw an exception in the collector because it's a terminal operation, this will also throw the exception on the collect itself, not on the flow. So for example, if you say print line it and then throw a runtime exception, let's say collect is bad. In this case, the application will throw a runtime exception upon the first actor, so we have flow finished, and collect is bad will interrupt the entire collection logic here, and this will terminate the flow as well. So these two items are probably quite straightforward. If you throw a runtime exception or any sort of throwable that's not being caught, that will interrupt the flow. If you throw an exception in the collect, that will also interrupt the flow. Okay. Now, naturally, in real life, whenever we want to obtain a flow, we don't necessarily emit all these values manually ourselves via the emit function. Maybe we want to obtain these values from external services, for example, databases or external APIs. And maybe those APIs throw some sort of errors because of contention, maybe some network errors or whatever. And it's often the case that we might want to retry obtaining that value from that specific API, which is why I'm going to simulate a realistic example here. So right at the top, when we have the first flows, I'm going to create a little interface. So interface, let's call this actor repository, assuming I can spell interface properly. Actor repository, and let's say that this actor repository has a little suspend fun. I'm going to call this find actors, and this is going to return us a flow of actor. Okay, now this actor repository may want to have a class that will extend that. So I'm going to have class my actor repository, which extends actor repository. And I'm going to override the find actors thing. And I'm going to have a little var, let's call this retries, starting at 0. And I'm going to put that as a property of this little class. And in this find actors method, I'm going to return a flow. So I'm going to say flow here. And let's assume that in this flow, I'm going to emit all these suckers. Not necessarily that they're suckers, they're rich and famous, and they also play superheroes, so whatever. So I'm going to say emit all these actors here. So I'm going to emit all the Justice League actors. And let's assume that if in the middle of this function, if the retries is less than 1, I'm going to say retries plus plus, and I'm going to throw a runtime exception, and I'm going to say should retry here. So should retry here, and assuming I can write this in a string. So I'm going to throw a runtime exception in the middle of emitting these 6 actors, and I'm going to ask the consumer of this flow to retry. And when the consumer retries, then this piece of code will not be true anymore. So this condition will not throw a runtime exception, and it will emit the rest of these actors. So the way that this is going to work is that the flow will emit the first 3 values, is going to throw an exception. I'm going to catch that. I'm going to retry, and upon the retry, I'm going to emit the rest of the 3 actors. So back in main, instead of the flows Spider-Man, I'm going to comment that out. And I'm going to say flows.myActorRepository. I'm going to instantiate that, and I'm going to say find actors. So if I say flows myActorRepository find actors, I'm going to say on each and collect. I'm going to do the exact same thing. So on each delay 1000, on completion print line flow finished. Let me also add on start. All right, so on start, we have flow started. On each, we delay by 1000, and on completion, print line. At this point, if I run this application, we're going to emit the first 3 actors, and the flow is going to crash, which is going to terminate my little flow. So we have Henry, Gal, Ezra. So we have flow finished, and we have should retry here. And in case we get an exception, we can add a little retry clause or a retry method here. So I'm going to say on start, on each, on completion, and I'm going to say retry to, which means that if we get an exception while processing an element, the retry function will make sure to reconsume the entire flow one more time. So if I run this application, you see flow started, we have actor 1, 2, 3, and here we got an exception, and then we got another flow started, meaning that the entire flow is being restarted. So look at that, we have the entire Justice League processed from the very beginning. So this is what retry does. Retry also takes a lambda as a last argument, meaning that from the exception that you're catching, you can decide to do something with it. For example, you can say print line, oops, exception thrown, retrying, and you need to return a predicate to say if the exception matches any sort of predicate that you want, you may choose to retry or not. So I'm going to say delay 1000, and I'm going to say true, meaning that I'm going to take the stream from the beginning. So let's run this one more time. So we have flow started, actor 1, 2, 3. We have oops, exception thrown, retrying. And after 1 second, we have restarted the flow and the entire stream is consumed one more time. Now, in the real world, we will probably use a more sophisticated back-off policy in which the delay is exponentially incremented so that we don't bring down a service from which we're consuming items, for example, a database or something like that. And there are versions of retry, for example, retry when and things of that sort, which you can use for that sort of scenario. Okay, so this is how we can process items or how we can recover from error if a flow throws some sort of exception. Another thing that I wanted to discuss is how to transform and work with flows. Because in terms of functional programming, flows offer the functional API that you see in collections. For example, the kind of map, flat map, filter, that sort of thing, we also have with flows. So let's assume that we have this Spider-Man flow, and maybe you want to transform from these actor data types and you want to transform their names and whatnot. You can say, let's call this Spider-Man names as spiderman.map. And the map API is very similar to the one that you see in regular collections like this, for example. And I can say it first name value to uppercase plus a space, and then plus its last name value dot to uppercase. And to uppercase is deprecated because the better, safer version is to say uppercase locale get default. I don't care about that. I'm just going to use the to uppercase just to make the code a little bit more legible. And this is going to be a flow of string, meaning that we transform every single actor in the actor flow into a string by virtue of this lambda. And this is very similar to the kind of stuff that you see on lists. So I can say, instead of flows my actor repository, whatever, I'm going to say Spider-Man names. So flows, Spider-Man names, and we can keep the same logic here. So flow started, we have Tobey Maguire, Andrew Garfield, and Tom Holland, all in uppercase. And because we have a while true, we are going to keep seeing them over and over and over again. So we have map. We also have filter, which obviously does the kind of stuff that you would expect. So we'll keep just the values matching or satisfying a predicate. That is a Boolean lambda. And a couple of other transformations that you can see on flows because they can be never ending are fold and scan. Now, fold works in a very similar way to lists. So for example, if I have a val, let's call this numbers flow, as flow of, and let's assume I have a bunch of numbers like 1, 2, 3, 4, 5, 6, 7, 8. The val, let's call this sum flow as numbers flow fold. And fold works in the following way. You pass an initial value, it's called a seed, and an operation that will take the seed as an accumulator and will combine that through this lambda to every single value of this particular flow. So I'm going to start with the fold at 0, and because the lambda is the second argument or the last argument in the list, I can take that out. I can say accumulator and value. I can say accumulator plus value. Now, fold, unlike the fold on lists, fold for flows is a suspend function. Therefore, we need to put that in some sort of suspend function. So I'm going to say suspend fun demo fold. I'm going to put this out. So because I'm having a suspend fun, I can do that. And at the end, what we get is a single number. So you can collapse a finite flow into a single value. Also, beware, fold works or it doesn't work for infinite flows. But there's no way for the compiler to check that, so this is up to you to be very careful with. So you can say print line sum flow, and I can comment this out, and in my main function, I can say flows demo fold, and you're going to see a single number being printed to the console, 36. That's going to be the sum of all the numbers 1 through 8. Okay, so that is fold. I'm going to also show you a suspend fun for scan, so demo scan. And scanning, instead of emitting a single number, will give you a flow of every single intermediate value of the accumulator as it's being combined to every single value of the numbers flow. So for example, if I create a val numbers flow, and instead of saying sum flow, I'm going to say, let's call this scan flow, and I'm going to use scan instead of fold. The signature is identical, but scan works in a different way. So let's assume that we have the number 0 as the original seed. The original seed is going to be subject to this lambda on the first value of the flow, and that's going to emit the first number, 1. Then this accumulator is going to be subject to this lambda on the second value. That's going to be 1 plus 2, that's going to be 3. Then number 3 is going to be added to the number 3. That's going to be 6. 6, then it will be combined with the number 4. That's going to be 10. 10 plus 5, 15. 15 plus 6, 21. 21 plus 7, that's going to be 28. And then finally 28 plus 8, that's going to be 36. So you're going to see all of these numbers being printed one by one. So I'm going to say scan flow dot collect, and I'm going to have print line it, just for you to see how this thing would work. So instead of demo fold, I'm going to say flows.demo scan, just for you to see how that would work. And we see all these numbers, even starting with the initial seed. So the initial seed is also being printed or being put into the flow as the first item. So 0, 1, 3, 6, 10, 15, 21, 28, 36. So this is how scan works. Scan and fold are very, very useful when you want to combine values in your flows. Fold works with finite flows, and scan works with both finite and infinite flows. We also have take and drop. So take is going to take the first n items out of the flow. Drop is going to do the opposite. It's going to remove the first items in the flow. So for example, if I say flows Spider-Man, and I'm going to say take 1, this is going to take just 1 item. If I say take 2, this is going to take 2 items. So this is going to return a finite number of actors here. So Tobey Maguire and Andrew Garfield, and after that the flow is going to be eliminated. Then if I say drop 1, I'm going to drop Tobey Maguire, at least at the beginning. So we have Andrew Garfield, Tom Holland, and so on and so forth, and then the cycle will begin again. So you can say take 1, drop 1, take n, drop n to take the first n items, or drop n items, the first n items out of the flow. These are super simple, and you can find those in collections as well. All right, so I think you got the idea. Cool. I'm going to remove some of this commented code, and I'm going to start talking about coroutines. So flows are inherently starting on coroutines and running on coroutines, but how about running the flows on separate coroutines as well? What do I mean by that? If I say flows Spider-Man names and so on and so forth collect, and I say print line Spider-Man in movies, and then I'm going to have another print line, Spider-Man in movies done. And the Spider-Man names, Spider-Man, I'm going to remove the while true. So I'm going to keep emitting just the 3 items here so that this flow actually stops at some point. Let me run this. So we have Spider-Man in movies, then we have flow started, Tobey Maguire, Andrew Holland, and then we have flow finished, and then Spider-Man in movies done. What does that tell us? This thing is a blocking operation. So this is blocking from here to here. Well, how about running the flow in its own coroutine? What about that? Well, we know about coroutines. We can start a coroutine scope, and inside this coroutine scope, we can put pretty much everything. And in the flow Spider-Man names and so on and so forth, when we want to consume that, we can consume that in its own coroutine. So we can say launch, and inside here, we can consume the flow. So let me format my code and let's import the extension function from coroutine scope. So I'm going to consume the flow on its own coroutine, and then the print lines will be on their own coroutine, which is the coroutine started by this coroutine scope. So if I run this, we'll see Spider-Man in movies and then Spider-Man in movies done on the same coroutine, and then the flow is going to be consumed on another coroutine. Now, launching and consuming a flow on a separate coroutine with a launch constructor is such a typical pattern that flows have an extension method to launch a flow. So I'm going to say launch in this. And the this reference is going to be the coroutine scope. But when you say launch in this, you cannot really call collect anymore. So I'm going to say on each delay 1000 and print line it, so that we also see the values there. So if I run this application one more time, we're going to see the same thing. So the print lines are in their own coroutine, and then we have flow started from flow finished, and the flow is being consumed on another coroutine. So we say launch in this. This essentially starts the flow consumption in a separate coroutine. Okay, so I'm going to take this this code out, and I'm going to put that in a suspend fun. Let's call this demo flow coroutine. And I'm going to put this entire code in there. And in main, I'm going to give you another example so that I can show you that flows can be executed or consumed within a separate coroutine context, which is a rich data structure with a bunch of information. So I'm going to start a coroutine scope again, and I'm going to take another flow. Let's say we have the flow of actors from Justice League. So I'm going to call this Justice League. All right. And in my coroutine scope, I'm going to have the following. I'm going to say print line, and I'm going to inject a special value here called current coroutine context. And current coroutine context is a coroutine context, which is nothing more than a map of specific data. And I can call get on this. So get means just indexing array style with a thing called coroutine name. So essentially, I'm printing out the coroutine name here, and I'm going to put that in between square brackets here so that I can identify which coroutine that this thing comes from. And I'm going to say before Justice League. And I'm going to do the exact same thing with after Justice League. And in between, you're probably going to guess what I'm going to do. I'm simply going to consume the Justice League flow. So I'm going to say flows Justice League. And then I'm going to say on start, and I'm going to do the exact same thing. So on start, print line, current coroutine context, I'm going to say inside Justice League. And then I'm going to collect it. So I'm going to say collect with print line it. So we say flows Justice League on start. So at the moment this flow is being consumed, I'm going to print this thing, and I'm going to print every actor in Justice League. So let me run this little application. We're going to see all these actors one at a time with no delays in between. So I'm actually going to say on each, I'm going to have a delay with, let's say, 500 milliseconds. So we can have all these actors printed 2 per second. So we have null. That is because the current coroutine context is empty at this point. So I'm going to say with context, and I'm going to have coroutine name, let's say main. I'm going to start this entire construct here, so coroutine scope, with the coroutine context wrapping it. We know this from the coroutines video, if you want to check that out. So right now, if I run this application wrapped with context, now we have coroutine name main, and the before Justice League, inside Justice League, and after Justice League all run within the coroutine name called main, and that's normal because, as I mentioned earlier, consuming the flow is generally a blocking operation. But I'm going to show you how we can make the flow run in a different coroutine context. So we can say with context and wrapping this flows Justice League. So we can say with context, and then we can say coroutine name Justice League now. And we can consume the flow in another coroutine context. So we can choose that. And in order to see an effect, I'm going to modify the Justice League flow to not emit all these values one by one. or emit them in a flow construct or flow of construct, I'm going to emit them manually. So I'm going to say, I'm going to wrap this in parentheses, emit, and I'm going to remove all these commas, and I'm going to put that. And I'm going to print line the coroutine context in which this Justice League flow is going to be executed. So I'm going to print line this little sucker. I'm going to take it out, and I'm going to print it inside the Justice League. So for now, we're going to have the with context coroutine named Justice League. And in this case, we're going to see something different in the console. So look at that. The inside Justice League has a different coroutine name. And running a flow in a different coroutine context is so popular that the with context is just too cumbersome to repeat over and over and over again. So I'm simply going to take out the coroutine name, and I'm going to simply say flows Justice League dot flow on, and I'm going to pass my coroutine name inside. So this is equivalent to me saying with context this little sucker. On each delay 500 collect print line it, and this is going to do the exact same thing. So we're going to see the same output to the console as we saw earlier. So this is how we can run a flow in a different coroutine context. Now, in this case, the coroutine context just describes the coroutine name, but the coroutine context can also describe the thread pool on top of which coroutines actually work. So if I go to the Justice League flow, and I'm also going to inject another value here, I'm going to say thread current thread.name, just to see where the JVM thread is that runs the Justice League. I'm also going to add this thread name here before and also after the Justice League. Currently, all of these things run on the main JVM thread. So if I run this application, you're going to see that the print also says or describes the main JVM thread. Now, in truth, the print line, the flow, and this other print line can all work on different JVM threads, and the semantic blocking will still be upheld. For example, I can say that this whole coroutine scope will run in the coroutine context described by the coroutine name main. I'm also going to add this to the dispatcher, which is the thread pool on top of which coroutines can work. So I'm going to say executors from Java, new fixed thread pool 8. So an execution thread pool as coroutine dispatcher, and this coroutine dispatcher is also a subtype of coroutine context, and these coroutine contexts can be combined with just plus. So this is a description that says where or how the coroutines wrapped inside can work, and the coroutines will work on a new fixed thread pool with 8 threads. And in this coroutine scope, I'm going to run the flows Justice League on another dispatcher or on another thread pool. So I'm going to say dispatchers.io, for example. Dispatchers.io I described in the coroutines video. Dispatchers.io is a good thread pool to run blocking computations in a coroutine. So for example, in this case, if I run this application, we're going to see different logs here. So we have coroutine name main, and the thread name is pool1 thread 1. The other coroutine is called Justice League, but it runs on a different thread pool. It's called default dispatcher worker 1. And the other print works on the coroutine name main on another JVM thread. So the prints work on different threads, on different JVM threads, and the flow is being consumed on yet another JVM thread, but yet the blocking or the semantic blocking between these operations is still upheld. So as you can see, these flows can run on different coroutines, and you can specify where and how these flows can work, which gives you enormous flexibility. So I'm going to say suspend fun. Let's call this demo flow coroutines. And I'm going to paste all this code inside. Okay. The next thing that I wanted to show you here is merging and racing. And to that end, I'm going to create a suspend fun. Let's call this demo merging. And I'm going to take another flow of the Avengers, for example. So we're going to have, for example, Justice League, and I'm going to have a val, let's call this Avengers, as a flow where I'm going to emit all the other actors, like Robert Downey Jr. and so on and so forth. I'm going to copy all of them, I'm going to paste them here. So I'm going to say emit these other people. All right. So we're going to have Avengers. Now, I'm going to emit all the Justice League and all of the Avengers, and I'm going to take this little sucker out, and I'm going to emit them at different rates so that you see how these things can merge. So I'm going to have a merge between the Avengers, so flows.Avengers and flows.Justice League, and the Avengers I'm going to say on each delay, let's say 200, and in this other one on the Justice League, I'm going to say on each delay, for example, 300. So this is going to be, let's call this heroes or superheroes. This is going to be a giant flow of actor that is going to have values from both of these flows, whichever comes first. So when we consume items from the heroes flow, we're going to consume item from either the first or the second flow, depending on which is available first. So I'm going to say on each print line it, and then I'm going to say collect. All right, so let's go this demo merging thing. So I'm going to say demo merging, and we're going to see items from both of these flows interspersed. So look at that. We have Robert Downey Jr., Henry Cavill, Gal Gadot, and so on and so forth from both of the flows, depending on how they are available first. So we can create different delays here, and we're going to see items one at a time or multiple at the time if you have different values for delay. So you get the idea. Now, as I mentioned earlier, the merged flow will consume item from either the first flow or the second flow, depending on which one comes first. There is another combinator, let's call this zipped, as flow Avengers on each delay 200. So I'm going to use this one. And then I'm going to use zip on the other one, Justice League on each delay 300. And the zip function also takes a combinator function between an item from the first flow and an item from the second flow. So I'm going to say Justice League and Avenger. I'm going to say Justice League to Avenger. I'm just going to create a little pair between them. And this is going to be a flow of pair between an actor from the first flow and an actor from the second flow. The difference is here, in this case, that a zip will only give us back a pair when both items are available. So when a Justice League actor is available and an Avenger is available, only then can we build a pair, and that is going to be pushed to the output. So I'm going to say zipped on each, I'm going to say print line it, and then I'm going to have a collect just for you to see how that would look like. So I'm going to cut the collect from the first one, so that will avoid consuming the heroes one. And I'm going to consume the zipped one, so that you see how that works. And at this point, notice that we have pairs, and they are available whenever the slowest flow is available for a new item. Now, this application is quite quick because the delays here are quite close, but let's assume that the Justice League was far, far slower. Let's say that we have Avengers emitting at 200 milliseconds and the Justice League emits at every second. Well, in this case, the pair will be available on every second, even though we're going to have Avengers emitted far more quickly. So look at that. We have pairs emitted every second. And finally, I want to show you flat map. Now, flat map for flows is going to be slightly more complicated than flat maps for lists because, for example, if I have a list like numbers, for example, list of, we have 1, 2, 3, 4, 5, and then if I say numbers expanded, I have numbers flat map, and for every item, I'm going to say list of x and x plus 1. This is going to give me back the list 1, 2, because we're going to have the mini list applied to item 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. That's going to be the list. So flat map on lists will simply expand every number to a mini list by applying this lambda on every single item, and all these mini lists are going to be concatenated into one big list. So flat map is quite straightforward for lists. Now, for flows, flat maps can take different flavors because flows themselves might not necessarily terminate in the same order that they're applied. So, for example, what do you want to do when you want to apply flat map on a flow? Would you like to have mini flows and have all these mini flows wait for each other so that you'll get all the items in order? Or do you want all the flows to simply push items concurrently? And the difference is between two versions of flat map. One is called flat map concat, and the other is called flat map merge. Let me show you what I mean by that. Let's say that I'm going to have an interface. I'm going to call this movie repository. And this movie repository will take a function, a suspend func. So I'm going to have a suspend fun. Let's call this get movies by actor or something like that. That takes an actor and gives me back all the movies that this actor has ever played in. For example, a flow of, I don't care what the movie data type looks like, maybe a movie data class, but I'm just simply going to return a string. So this is the API. And let's assume that I'm going to have a class. I'm going to call this my movie repository. And this extends movie repository. And I'm going to have a little private val. Let's call this DB so that I don't have to use an actual database. And I'm going to have a map of, and I'm going to take a bunch of these actors. For example, I'm going to take Robert Downey Jr. So Robert Downey Jr. is going to have a list of, and Robert Downey Jr. is going to be associated to a list of, for example, Iron Man. And then we're going to have Avengers, and then we're going to have Infinity War, and things of that sort. Then let's assume we're going to have Gal Gadot, for example. So Gal Gadot is going to have a list of, and we're going to have Wonder Woman, and then maybe Justice League. And let's take another one, maybe Ben Affleck or something. So Ben Affleck to list of, and Ben Affleck played in Justice League and Argo, for example. Amazing movie. Now, let's override. So we're going to override get movies by actor, and we're going to take whatever the database gives me back. So if DB contains actor, then I'm going to say DB actor, and this is going to be a list. And then I'm going to say as flow. And then I'm going to say on each, I'm going to delay 1000. So I'm going to obtain all the items from these lists one at a time with 1 second delay between them. Otherwise, I'm going to simply obtain an empty flow. So otherwise, I'm going to say flow of, and I'm going to keep it at that. Now, I don't care about the code style too much for this particular implementation. I'm just going to force this to be a non-nullable because I've already checked whether the actor is in the database. So I'm just going to use the nullable forcer here. And I'm going to use this my movie repository to obtain flows of strings. So here goes nothing. Here under flat map concat, I'm going to say val, let's call this flat mapped movies as, and I'm going to take all the Avengers. So I'm going to say flows Avengers on each delay 200. I like that. So flows Avengers on each delay 200. And then flat map, and then notice that we have two flavors of that, flat map concat and flat map merge. There's also flat map latest, which is a different flavor. I'm going to use concat and merge. These are the two most popular. So flat map concat, and for every actor, I'm going to return the flow obtained by that movie repository. So let me instantiate that. So movie repo as my movie repository. So I'm going to instantiate that as movie repo dot get movies by actor on actor. And here we're going to have this flat map movies as a flow of strings. So I'm going to print it out exactly as it is. So I'm going to say flat mapped movies, collect, and I'm going to say print line. So collect print line it. And I'm going to cut the other collect out, just for you to see how flatmap concat works. So in flatmap concat, the mini flows that are obtained by the lambda will wait for each other so that the order is maintained. Let's see how that works. So we have Iron Man, Avengers, Infinity War. That's for Robert Downey Jr. Well, that was unfortunate because we have a single Avenger in my movie repository. We can swap that for Justice League. So let's use Justice League instead. So Justice League. And let's run this again. So look at this one. We have Wonder Woman, Justice League, and then we're going to have Justice League Argo. That is for Ben Affleck. So we have Wonder Woman and Justice League. That's the flow for Gal Gadot. And then we have the entire flow for Ben Affleck. So the flow for Ben Affleck waited for the first one to finish before it could continue. Now, it's probably best for debugging purposes in this get movies by actor I return a string which also contains the actor itself. So I'm going to have db as flow on each, and then I'm going to have a little map. So map, and for every movie, I'm going to return a little string where I'm going to take the actor's full name. So I'm going to have my actor.fullName, which is a method that I haven't added yet, and then the movie itself. So I'm going to have my movie. Okay, let's go to my actor and let's add a little method. So fun full name, and I'm going to return first name value plus a little space plus last name dot value. All right, so that's going to be my full name thing. All right, so at this point, if I run the application one more time, we're going to see the Gal Gadot movies and then the Ben Affleck movies. Okay. Now, if I change flatmap concat for the other version of flatmap, which is flatmap merge, with the exact same lambda, all these mini flows are going to intersperse. So they're going to generate items concurrently. So we have Gal Gadot Ben Affleck, Gal Gadot Ben Affleck. Notice that in this case, the output is intermingled. So there you have it, folks, a long-form introduction to Kotlin Flows. I hope you enjoyed this video and found it valuable. If you did, go ahead and click the like button for me and subscribe to the channel for more videos like this. And check out my website at rockthejvm.com. I have literally hundreds of hours of everything that you can imagine in the Scala and Kotlin ecosystems and much more in the future. So until next time, this is Daniel signing off.